material simplifications. And so first we talked about incompressible. For us, we just use that with liquids, but we'll pretty much always be able to use that whenever we have liquids. And the assumptions related to this are that the specific volume is constant. The specific internal energy is just a function of temperature. And C, which is CV and CP, is D, specific internal energy, D, temperature. And we did an example or two. So now we're going on to ideal gases. Ideal gases. And since I have the assumptions for incompressible up here, I'm going to write out the assumptions. So here there are 3 of them. We're going to have 5 of them for ideal gases. And I'll just write them out and then we'll go into what they mean and stuff. The first one is the ideal gas law. This is going to be a little different form than you saw in chemistry. And we'll talk about why that is and what this all means. But we have the pressure times the specific volume is equal to a gas constant times the temperature. Okay. It's missing the number of moles, I think, from what you probably used in chemistry. It just has to do with the way we define all this stuff. The key thing is that R is not universal anymore. It's particular to your gas. Okay, so that's something you have to calculate for your gas. But the benefit of writing it this way is we have the specific volume instead of the true extensive volume. And so that's something we can look up in tables or on the website or whatever. And then the second one is just like with incompressible materials, specific internal energy is only a function of temperature. For ideal gases, no, I'm getting ahead of myself. The third one, let's say, is that the specific enthalpy is only a function of temperature also. And you can always calculate it as the specific internal energy plus that gas constant times the temperature. Well, you can see that right away where that comes from. If PV is equal to RT and the definition of specific enthalpy is U plus PV, then I've just made that one little substitution. And now for the specific heats, they're not the same anymore, but they are both simplified. So the constant volume specific heat is dU temperature. So that has the same definition as both specific heats for incompressible. And then the fifth one is the constant pressure specific heat is CV plus that particular gas constant, that constant for the gas that we're using. Okay, so first of all, the ideal gas law. The one you've seen we would write this way. The pressure times the extensive volume is equal to the number of moles times the universal gas constant that I'm going to write with an overbar because that is a specific gas constant dependent on, per mole. So we use that overbar for specific constants, uh, intensive values that are per mole. Okay, so that's what the overbar means.
Wait, so R with the bar is universal
Yeah, right.
and non-bar R is like for
Specific
each
to a
substance?
individual substance, correct. And then times T. Um, so this is okay, so R bar is the universal gas constant. Um, and R for us is the universal gas constant divided by capital M. And capital M is the mass um, per mole of our specific gas. Um, so you can read this off of the periodic table. Um, so you can think of this as the periodic table value uh, times 10 to the minus third. And that's because the periodic table tells you the number of grams per mole for a substance. Um, we want kilograms per mole because we want SI units. And a mole is 6.022 times 10 to the 23rd molecules of whatever gas you have. Okay, so if we make this substitution of our specific gases gas constant, we can think of this as P V over M is equal to N times R over M times T. And then this turns into P little v total mass divided by the number of moles cancels with the per mole basis here, and we get RT. So this is the form that we're going to use. We don't have to know the number of moles, but the downside is we have to figure out what that is for each substance that we use. I want to do an example using the ideal gas law. So let's say we have 0.5 kilograms of air, which we're going to treat as an ideal gas, in a fixed tank. And we're going to add heat to it. And it goes from an initial temperature of 20 degrees Celsius and an initial pressure of 1 atmosphere of pressure to a final pressure, but we're not given the temperature, 2.02 times 10 to the fifth pascals. And we want to calculate first what's the volume of the tank. And second, what's that final temperature? Well, at state one, we can use the ideal gas law. We're given that we have a pressure in SI units of 1.01 times 10 to the fifth times the specific volume is equal to R times the temperature. Notice that in the ideal gas law, the temperature does not appear as a difference. So we have to convert temperatures always to Kelvin. So we're starting at 20 degrees Celsius. In Kelvin, that's 293 or 293.15, you know. In order to calculate the specific volume, all we have to know now is what that R is. So what do we know about air? So we need R for air. And in this class, we're always going to assume that air is 80% N2 nitrogen gas. And 20% O2 gas. So we can think of the total mass per mole as 0.8 times the mass per mole of N2 gas plus 0.2 times the mass per mole of O2 gas. For N2. So how do we figure this out? If you look on the periodic table, it says that one nitrogen atom has a mass of 16, 14, grams per mole. Okay, you can just look that up on the periodic table. We have two of those in N2. So we're going to go 2 times 14. That's what it says on the periodic table. We want kilograms per mole, not grams. So we're going to multiply times 10 to the minus 3. And so this is 28 times 10 to the minus 3 kilograms per mole. For oxygen, it's O2, so we have 2 atoms. So 2 times. The periodic table says 16 grams per mole for oxygen. So this is 16 times 10 to the minus third. And so you get 32 times 10 to the minus third kilograms per mole. And so now combine these. And for air, we get that the kilograms per mole for air is 0.8 times 28 times 10 to the minus third plus 0.2 times 32 times 10 to the minus third. And we get a value of 28.8 times 10 to the minus third And so now the R value for air is the universal gas constant, 8.314 in SI units, divided by the mass per mole of air, 28.8 times 10 to the minus third, and you get a value of 289. And this has units of joules per kilogram Kelvin. That's SI units for that R value. So now we can go back to the ideal gas law. We have 1.01 times 10 to the fifth times the specific volume is equal to 289 times 293. And so this is the specific volume at state one. And so the specific volume at state one is 0.838 cubic meters per kilogram. Well, we wanted the extensive volume of this tank, but if you know the mass, you can go back and forth between extensive and intensive. So the volume of the tank is the mass. I said it was 0.5 kilograms of this gas times 0.838 is equal to 0.419 cubic meters. So that was, this was all to calculate the volume of that tank. But since it's a fixed tank, the volume doesn't change. And if the volume doesn't change, the specific volume doesn't change. So now that we know the specific volume at state one, we also know it at state two. So now we want to calculate the temperature at state two. But we know that V1 is equal to V2. And so now the ideal gas law says the pressure at state two, which this time is 2.02 times 10 to the fifth, times the specific volume at state two, which is the same as state one, is equal to the R value for air. That doesn't change based on anything having to do with the state. That's the same for, so you can use that 289 anytime you see air in any problem. Times T, and so now we can solve for T. This is the T2, and so T2 is equal to 585.73 Kelvin. Subtract out 273 if you want to see what it is in Celsius, and you get this is 312.7 degrees Celsius. Any questions about that?
And then the percentage of air will be questions involving water vapor or other things that might be in the air?
Well, this is for dry air. That's a good question. So this is for perfectly dry air. If you knew the fraction of water that was in the air, you could include that in this. So yeah, moist air you can still treat as an ideal gas.
Is it relevant type of concentration of if there was like a high percentage of water, would it affect the calculations? If it was calculated as dry, but had a high concentration of moisture?
Yeah, it would. Yeah, I mean, it would have. It would affect that R value, and so it would affect all your calculations. Yep. It would also affect like some of the other things that we're going to use. It would affect. So remember that when we did incompressible materials, we looked up that C value in a table for the temperature we wanted. It would affect the CV and CP values that you would look up. And so, yeah, it would affect things. Okay, one thing I want to say is notice. For liquids, we use the fact that C was equal to du dt, and the fact that C is fairly constant with temperature. You know, it's not constant. We saw that it varies a little bit as you go from 0 degrees Celsius to 25 to 50 to 100, but it's fairly constant as the temperature changes. To calculate relationships between the specific internal energy and the temperature. Okay, that's something you can always do with liquids, and something that that you did in Physics 1, most of you. Okay. For ideal gases, it looks like you can do the same thing. Using the fact that the constant volume specific heat is equal to du dt. Okay. But CV varies a lot more with temperature.
Professor?
Yeah.
So at the top it says ropes. What is that?
Relationships.
Okay, really?
So only do this for small temperature ranges. Well, you might think, okay, if CV only depends on temperature, which it mostly does, you might think, well, why couldn't you curve fit what CV is at different temperatures? And then you can still find a relationship between specific internal energy and temperature. You know what I mean? Like come up with a polynomial curve fit of CV with the temperature. Maybe you're like, God, I didn't think that. But, you know, uh, so say you have this curve, it looks kind of like a parabola or whatever. Like maybe your first guess would be like, let's just make curve fit a parabola to CV as a function of temperature. And then we'll use this relationship and just come up with a little more elaborate relationship between specific internal energy and temperature. And you can do that, and people do that. So I don't think we have any problems in this class where we do that, if I remember, but the same principle applies it just doesn't work very well if you treat CV as constant, unless you have a very small temperature range of like less than 10 degrees, say, or something. Okay. So when I say small temperature ranges, let's say less than about 10 degrees Celsius, question mark, like it really just comes down to what amount of precision you require. The bigger the temperature range, the worse that approximation is. Um, well, where do assumptions 4 and 5 come from? We can figure that out. So we can go back to the definition of CV. Remember, CV is defined by this partial derivative thing. It's the partial derivative of U with respect to temperature, um, holding the volume constant. Well, for an ideal gas, U only depends on temperature. So it just immediately becomes a total derivative. You don't have to worry about partial derivatives unless you have more than one independent variable. So right away you can see that CV is equal to the total derivative du dt. Okay, so that's the first one. What about the second one? Um, so Cp is equal to, the definition is the partial derivative of the specific enthalpy with respect to temperature holding the pressure constant. Um, and so this is the partial derivative with respect to temperature of U plus PV, P little v. That's the definition of specific enthalpy. But we've already replaced that with RT from the ideal gas law. Let me put that step in. You guys, I can tell how fascinated you are right now, but I'm trying to make a point about how to kind of remember these, organize these in your head that I'll get to when I'm done here. So this is for a constant pressure. The ideal gas law says this is equal to the partial of temperature, partial with respect to temperature of U plus RT for P constant. Well, we know that U is only a function of temperature. RT obviously is only a function of temperature. And so we can write this as the total derivative of U with respect to temperature plus the total derivative of RT with respect to temperature. Now that's just a derivative you can take, and what you get is du dt plus R, which is just what we got for CV plus R. So all of that is stuff that you can reason your way through. So the point is, if you remember the ideal gas law, and the fact that the specific internal energy is a function only of temperature. All the rest, the other three, are pretty easy to derive. Okay, so if you ever forget what those 5 assumptions are and you're not given what they are, or your notes are too far away or whatever, remember that based on these 2 things, everything else has to follow. Okay. Anybody have any questions about that? Those are the 2 main assumptions that we're going to make in this class: incompressible materials for liquid and ideal gases for vapors. Okay, so now we're getting into the next topic. And that is control volume analysis. And for now, this will include 2 things. The first one is conservation of mass, which we'll also call mass balance. And the first law of thermodynamics. And most likely from your Physics 1 stuff, this is going to be a little bit foreign, this control volume analysis. So what we're talking about is when you do physics, what you do is you pretty much always, what you've done up to this point is you've always taken a set amount of material, a ball or a skier or whatever, a set amount of material, and followed it around as it moves. Okay? But often when you're dealing with fluids, and fluids are gases and liquids, so either gases or liquids, there's really no way to track. If you think about, like, how would I track? So say that I have this gas that I want to track, but it's going to go through this machinery and spread out into a room and all this stuff. How would we go about tracking that material? And so instead of tracking the material itself, what you do is you pay attention to a certain volume, okay? And then you just pay attention to the material that's coming in and the material that's going out in addition to your volume. And you can use the laws of physics just by looking at that control volume, okay? So this is useful for fluids, which means gases and liquids. And instead of tracking a set amount of material, we're going to track what happens in a control volume and what material is entering the control volume, and what material is exiting the control volume. Okay, so I'm going to start with the mass balance, conservation of mass. By the way, you know, we haven't started talking about entropy in the second law of thermodynamics yet, but after we do that, we'll use a control volume approach for the second law of thermodynamics also. But it's always the same principle. You track a set location, and you track what goes in, and you track what goes out. So for the mass balance, let's imagine we have like a tank. And we'll think of an inlet and an exit. And there's some mass inside the control volume. And there is some mass coming in. This is the material going in. And then there's material coming out. And so the control volume conservation of mass says the rate at which the mass in the control volume changes, so dm dt inside the control volume, is equal to the rate that mass comes in minus the rate that mass goes out. That's a pretty sensible requirement. So there's no mass created or destroyed inside the tank or whatever it is that means. So the meanings of these things, dm dt for the control volume is the rate of change of mass inside the control volume. M in is the rate of mass flow into the control volume. And M dot out is the rate of mass flow out of the control volume. One thing that's going to be really useful for us, this is going to come up pretty often. So one very useful formula is that at either the inlet or the exit, the rate of mass flow is equal to the area of the opening times this capital V in this case doesn't mean volume, it means the average speed of the material going in, divided by the specific volume. Okay, so let me write those meanings down. So this works for the inlet and the exit. A is the area of the inlet or exit. V is the speed of the material. And actually, let me make this clear. This is the average speed. Of material entering or exiting. And little v is the specific volume. And you can make perfect sense out of this if you think of like the Play-Doh Fun Factory. Do you know what that is? You guys know what Play-Doh is? Well, back before cell phones, we used to have hours of fun with this thing where you'd put Play-Doh into a thing with a little pump, and you'd put an aperture in front of it that was a certain shape, and you just extrude Play-Doh through this thing. It would come out like a flower cross section or a heart cross section or whatever. That's the Play-Doh Fun Factory. And so think of the material, even though we care about fluids. Think about like Play-Doh coming out of an aperture. So think of material coming out of a hole like this. Okay, so say it's going this way. And this could be either leaving the control volume or entering the control volume. And let's say this length is L. This is the area of the hole that it's going through. So at a single instant, the mass of that Play-Doh that's come through there so let's call this the mass of the extruded piece. Is the volume times the density. And the volume is the area times the length times the density, which we can write as A times L divided by the specific volume. Okay, well, now if we want the rate, that this is coming out, then we'd take dm, so this is our m. So dm dt is equal to d dt of a l v. Well, a and v don't change in time. And so you just get a over v times dl dt, and dl dt, if you think about it, is just the speed. So this gives you a times capital V over little v. Okay. But that's going to come up so often that you're going to probably just want to remember that. And on tests, I'll give you that formula. Okay, I'm over. That's all. Goodbye.
For some of us,
Some of you have to go to another class now, correct?
called static.
Yeah. Bottom.